Yeah, I mean, and before I even start, I mean, I think of this as we go through this as an extension of what the core offers, because, you know, what I'm going to describe to you is, I mean, my gosh, I could not have asked for a better introduction as a prelude to my talk. So some of the things that you're going to hear about are designed to accelerate, you know, some of the manual nature of what you just saw in the previous talk. And so think about this as something that, you know, previously the entry point to do some of these analysis was very high. And so the goal of this software is to actually drop that down. And I'll show you some data from some of our collaborators where they actually went from, you know, their standard analysis time for one of these studies with about 15 data files was 2 weeks time. And so using this workflow, we can actually drop that down to only a couple of hours. So the productivity that you can have from your laboratory, the time to getting your results can be greatly accelerated. So with that, I will start out with just a marketing slide because they feel like I have to put a marketing slide in. So but I'll give you just a quick introduction. And these are all tools that are in the core right now. And, you know, as Maureen mentioned, we'll have another one shortly. So, you know, Agilent has been a major player in the metabolomics world for the better part of a decade now. And we've had some innovations that I think have really helped us in this space. We start off with, and we recognize the need for identification. So we've developed about 10 years ago, we developed the Agilent Phen Electron Impact Library. A couple of years later, we developed the Metlin LCMS library with Gary Patty and Gary Schusdak. So we start off with some tools that would help us do the identifications, the annotations of metabolites that we found, or features we found biologically relevant through our statistical analysis. So, you know, something's just a feature until you can identify it, right? And we heard Gary talk about yesterday, there's a huge number of features that we can find, but we cannot assign an identity to. So after we developed a couple of libraries that can help us with this, we moved on in about 2010 with the release of Mass Profiler Professional, which is a very in-depth chemometrics program designed to do all sorts of statistics and visualizations to help you interpret your data. As a side component to that, we also have released at the same time a piece of software called Pathway Architect, which is an extension of that allows you to take what you found to be biologically relevant from your statistical analysis and cast it onto a canonical pathway. So now you can start to see visualizations of what's going on in your biology. And then a couple of years ago, we started getting requests for a batch feature utility that would take the raw data, take the first data reduction step, and expedite that for us. So take it from a raw data point to a compound feature information type of a format. And so we released this piece of software called ProFinder in this regard that does batch feature extraction. And Maureen, as she already mentioned, will talk more about this from the untargeted perspective tomorrow. I'm actually going to talk about today in more of a targeted light and how we do it and apply it to flux analysis. And so about 2 weeks ago, we released the latest innovation from Agilent in metabolomics, which is VistaFlux. And this is designed at metabolic flux analysis. So thanks to the wonderful, wonderful introduction, I don't need to spend a lot of time here. But think about flux analysis as something that's going to extend your metabolomics insight. So it's going to be kind of a step 2, as you've already heard about. So step 1, in most cases, is going to be doing a standard metabolomics, type of a characterization to learn about the metabolites that are upregulated, downregulated, build a skeleton, if you will, of your pathway and see what's going on with the metabolome. What we're going to do with flux analysis is be able to track that flow of those metabolites through those pathways. And so it's often good to consult with the local and the not so local experts. And so when you're going to be the first to market with a new piece of software, it pays to consult with the experts. And so I like this quote from Nikolai Zamboni. It's from ETH Zurich, and it kind of paints a nice picture of what flux means. And so his comment is, flux analysis elevates metabolomic studies to a different level. And so while metabolomics will report on the molecular composition of a cell, flux analysis gives us the in vivo pathway activity. And so the way I like to think about this is metabolomics is sort of like an X-ray, right? You can get a lot of information. You can get a lot of content about the composition in your metabolome. Flux can be thought of as kind of like a CAT scan. So there's a lot of times where an X-ray will answer the question or address the problem, find out what the problem is that you have. As a step 2 to that, in many cases, if that doesn't give you enough information, you're going to go to something like a CAT scan that will actually dig deeper. So one of the examples that Gary Patty actually showed yesterday, and I'm just delighted that our data actually matches what his said, because that would be really embarrassing if it didn't, well, we're going to talk a little bit later in a data set about the TCA cycle and following the flux pathways through. And so in many cases, we see as glutamate would enter the TCA cycle, and it would do so in a clockwise fashion. In certain cancers, in this case, the data we're going to show is in chondrosarcoma, there's actually an alternative pathway that we see from the uptake of glutamate. And with one of our collaborators, Justin Cross from Memorial Sloan Kettering, was very kind to provide us with some data that we could use and present upon. I'll touch on how the software workflow actually was able to tease out this metabolism in the cancer cell line. So quickly, what is VistaFlux? So we're going to be doing the stable isotope tracking of C13, N15, or deuterium. And this is one at a time. We're not going to do mixing right now. And this is Agilent LC-TOF and Agilent LC-Q-TOF. There are certain assumptions that we have to make about this algorithmically, and so it's really difficult to develop the software for an open platform. And so because there's certain things that we know about our mass spectrometers, and we can obviously test thoroughly with our instruments. So it is not going to support GCMS at the first release. That is in the works. It's something we're very interested in doing, but it will not at this time do anything except LC-TOF and LC-Q-TOF. As a second component of that, you heard a little bit about isotopologues and isotopomers. So this software at this time, the first release, is going to deal only with isotopologues. And this is for 2 reasons. One is because it's very challenging, it's very computationally challenging to do isotopomers. As you heard, it requires MSMS, GCMS, NMR. And there's actually, the feedback we got from our collaborators is there's a lot of information we can glean from isotopologues. So this is going to allow us to be able to say, we can feed in this case, so this is fumarate. So it's a C4 metabolite, and you can see at 0 hours, we're at natural abundance, right? So we have 99% C12 and 1% C13. If we incubate for 8 hours in fully labeled C13 glucose, we can see that the profile changes quite readily. And so what we're able to do is we've put across a naming convention here that hopefully I'll get across right now. But so consider the natural abundance as your N+0. So you're going to have no C13 and 4 C12s, all the way up through, in this case, so what the N+4 would represent is that we have full incorporation of 4 C13 atoms into fumarate after 8 hours. So does that make sense? Well, should be pretty straightforward. So that's what we're able to do. We're able to track the isotopes through the pathways, but we are not going to be able to determine the precise position that carbon is on the metabolite. And thank you again for the nice introduction, because it saves me some time talking about this slide. So, in the past, this has been a very manual process. And so you're going to start out by creating a target metabolite list. You're going to calculate all the possible M over Z's for those isotopologues. So you're going to say, I have fumarate at C12, and you're going to have to calculate what would happen if one of those was substituted with a C13, 2, 3, and 4. Then you're going to have to extract the chromatograms for all of those isotopologues for all of your metabolite targets. So let's say you've got 15 or 20 metabolite targets you're looking at across however many data files you're looking at. Then you're going to need to integrate those peaks and basically transfer that to a spreadsheet like you saw. And then review the results, see if they make sense to you. And then as the last step for visualization, this is done in many ways. It can be as simple as in an Excel. There's some open source software, Cytoscape, Adobe Illustrator, etc. But these are all usually open source, limited support type of visualization tools. And so we wanted to be able to provide a piece of software that could do all of this in a time-efficient fashion and be supported. We wanted to be able to have resources in-house that can train people on how to use the software and advance science, if you will. So the VistaFlux workflow starts off with you're going to still create your target metabolite list because that's reasonably important to know what you're looking for. As Chuck's mentioned, as we've heard throughout the last couple of days, it's very important to know something about your biology, not go in just blind and do an untargeted experiment. So we're going to create a target list of metabolites based off of the biology we're hoping to probe. So for example, if we're looking, if central carbon metabolism is of interest to us, we're probably going to go and look for the metabolites associated with glycolysis and the TCA cycle. So acquire data, talk a little bit about how that's done, and then we're going to do all the data extraction in ProFinder and follow it up with visualization on the pathways with a piece of software that we've designed called Omics Premium. So at this point, I'm going to give you kind of a more technical overview of the workflow. We'll spend a little bit of time algorithmically how we're extracting the isotopologs. And at this point, I know there's going to be some guys in the audience and gals that are going to have a couple of questions. So I would say go ahead and spit them out for the algorithms, and the odds are I won't be able to answer them anyway. So, so I've alluded to this already. So you're going to specify a list of metabolites, right? So back to the central carbon metabolism example, you look for the TCA cycle and you look for glycolysis. So by that logic, we came up with a piece of software called Pathways to PCDL. And the premise here is that this is a utility that has pathway content from Biopsych, Metapsych, KEGG, and of course Wiki Pathways. And so you can select the pathways that you're interested in and pull down the metabolites that would be associated with those. Now at this point, that allows you to pick the biology you're interested in, but it doesn't give you much information because at that point in the pathway, it's just a name. It just says D-glucose. And so you need a reference library in order to be able to add some information to what those metabolites are and what they mean. So something like the Metlin library that we have produced with Gary Patty and Gary Schuzdak is very helpful here because it has MS level information, MSMS, should we need it in the future. It will have structures, it has identifiers, and most importantly, if you've been curating your library appropriately, it will have retention times because you need those for the isotopolog extraction. So after you've referenced Metlin and you have all of your identifiers present and everything, and you've built your metabolite list, the last thing to do is really to select your tracer. And as you've already heard, this can be accomplished in many different ways. You may try different tracers to probe different entry points on a pathway. And so, for example, if you're going to probe glycolysis, you're likely going to start with fully labeled C13 glucose and watch it perfuse through the pathway gradually over time. So you'll determine your tracer, and one additional point is that ProFinder also allows you to determine the purity of that tracer, because if you go to Cambridge, for example, and you order U-glucose, it's going to be 99%, 99.5%, whatever. So that affects the calculations, right? We've already seen that when we do the natural abundance correction. So important thing to consider. So data acquisition. What do we do here? So this is a high-resolution instrument, and despite the fact that this is a targeted workflow in that we are doing targeted data analysis in ProFinder with our metabolite list, we still acquire data in an untargeted fashion. So this is LC-TOF or LC-QTOF in a MS scan mode. So we're still going to pick out all the information in the entire data analysis run, which is nice because we can also go back later and with some more data analysis process different pathways. If we came across something else that was biologically relevant to us later, we just go re-mine the data. We don't have to reacquire the data. So there's three things to really keep in mind here. It needs to be a high mass accuracy and high resolution instrument, obviously, because you need to have good mass accuracy and accurately measure the isotopal logs. But if you guys think about this, we're going to be measuring isotopal logs. What do you think the single most important or perhaps single most sensitive parameter is that a mass spectrometer needs to have in order to do this well? It's on the slide if you need help. Second one on the list. So isotopic fidelity. That's the ability to accurately measure abundances. That's to be able to take fumarate at C12 and say that C12 is 98.9% and the C13 peak is 1.1%, and do it accurately every single time, because we're measuring the incorporation over time of isotopal logs. So these are going to go up, they're going to go down. If our accuracy here is 5% or 10%, that's directly correlated to our results. That's 10% error. The last thing is dynamic range. And I think Gary mentioned this. I took his short course last year at ASMS so I could feel, in touch with, with his research. And so, he made the comment that, there's about 10 to the 12th concentration range in, the metabolome. And so mass spectrometers can at best, very best, measure the top 5 orders of that, right? So you want a mass spectrometer that has the absolute most dynamic range that you can possibly get, because the metabolite pools are going to vary greatly in concentration. And then, of course, there's a couple of recommendations that the marketing people put in. So 6545 were released last year at ASMS. I'm actually very, very pleased with the data coming off of it. It's rock solid. And then for labs that actually have a QTOF, in many cases, then some of the data you're going to see was obtained on a TOF, because you're doing scan only right now, and a TOF will give you quite good data as well. So it's not necessary to go out and buy a huge high-end instrument even. So I want to talk a little bit about ProFinder now. And as I mentioned, Maureen will discuss the kind of the untargeted side of the fence, and I'm going to discuss the targeted side as it applies to fluxomics. So ProFinder is, as I mentioned, was released about 2 years ago as a batch processing utility that allows us to do many data files simultaneously. So it is now multi-threaded, so we can take advantage of multi-core PCs, and we can process up to about 500 data files, QTOF data files at a time. So we can chuck them up, go have our coffee time, and come back, and we'll have data that's been extracted for us. So with that in mind, we will take the metabolite list that we generated, along with the data, and feed it into ProFinder, and it's going to mine it automatically for you for signal. So the results are then presented to you in 3 places. So we have the chromatogram here, and we're looking again at fumarate to keep everybody on task. We'll see our mass spectral results, and you can see at time 0 we've got no incorporation. At 8 hours we've got a significant growth of the fully labeled M+4. And then we also have a bar graph representation of this. We can have error bars, and we can do it with the corrected natural abundance correction. etc. So at this point, I want to talk first verbally about how we're extracting the data, the isotopologs, and then we'll go into an actual example because this is kind of complex, and it's really good to look at this in a couple of different ways. And so from the target list that we had where we said, here's my 15 metabolites, and I'm using a C13 tracer, the software is going to go through and it's going to calculate what each possible isotopolog could be. So it'll take that and it's going to extract the chromatogram for each one of those possible isotopologs along with the specified retention time that you gave it. And we're going to do this with a slightly more permissive M/Z tolerance and retention time tolerance. So it's kind of a two-stage process, and that's why it says a multi-stage algorithm, because we're going to start wide, if you will, let the algorithm find things, and then if you can imagine looking through a pair of binoculars, then you're going to zoom in on them once you've actually found them, because it's awfully hard to try to zoom in on the moon with a telescope before you found it in the, So we'll do that. We'll integrate those EICs, and then we're going to start to narrow our tolerances and refine the data. So we'll extract the MS at that point, disqualify ions that don't meet the criteria, and create a new EIC. So then we start doing some scoring, and that's based off the number of qualified isotopolog ions, their relative abundance, and how close they are to the target retention time. So at this point, we've arrived at the raw isotopolog abundance. But as you've already heard, it's quite important to do a natural isotope abundance correction. And that's where we use the tracer that we specified in its parent purity to calculate that. And this is all done in situ while it's processing. So the benefits here are that we're extracting EICs instead of doing just a raw mass spec, looking at the raw mass spec signal, and so we're not being confounded by noise and background and things, and so that decreases our false positives and gives us basically more accurate results. So now I'll give you a real example, and as you can see, the data that we're seeing here is reasonably complex, and so at this point you might start to kind of understand why we're not just jumping right into isotopomers and then targeted analysis. We kind of needed to stick our foot in and get our feet wet a little bit with flux analysis, algorithmically speaking, because it is very challenging. So what we're looking at here is this is a trace of EICs, and so along the bottom here you can see all the way out to an M+7. So this was a 7-carbon metabolite that we were looking at. The dark black trace here represents the total sum of those EICs, so that's everything together. And so what you can see here is, if you just look at this, visually, there's about 4 different places where our data could really live. 1, 2, 3, and 4. So first thing we're going to do, just like we talked about, is we're going to start wide and we're going to narrow down. So, and hope we get a refinement. That's the big thing, right? So if we cramp everything down and it still looks like this, we're going to have a problem. So whenever we do that, we actually do get a refinement. Our spectra looks somewhat more simple now. And we can actually start to make some sense of it, or the algorithm can. We don't see any of this part. And so if you look at peak 1 now, this is just an unlabeled isotope cluster. So the molecular ion and a natural abundance, not the natural amount of C13 that you would expect to see, 1.1%. Peak 2 is actually completely eliminated because after we narrowed things down, it did not have any qualified ions that met the MZ tolerance. Peak number 4 failed the coelution test because, as you've heard, these are isotopes, so they should, in practice, completely coelute. The only time where this may be a slight issue is with deuterium, because it's a little bit greasier, and you can somewhat get a little bit of separation if you have a huge incorporation of deuterium. It's a problem for lipids, for example, where you may have an entire fatty acid chain that's deuterated at some point. But bottom line is, peak number 3 won because it was closest to the expected retention time we wanted to see, and it had several isotopologs that were of the correct mass to charge ratio. So does that make sense, or did I I mean, I see some eyes, so I guess not everybody's asleep. So is that good? Is that good? Okay. So now that we've done all this data extraction, and it took roughly about 90 seconds for, so even on my humble PC, I've processed about 15 data files with 17 targets. It takes about 90 seconds. So this part is very fast. We can visualize the results on our software that's called Omics Premium. And we're going to go into some details here, but I'm going to save most of them for when we actually look at some real data. So for now, what you're seeing here is the TCA cycle on with glutamate. And I'm zoomed in again on fumarate because I want to keep everybody on point. We don't want to forget fumarate. And so this is a quilt plot, and this is one of the many visualization tools that we have in Omics Premium. Some of them are what I will say very quick and easy, so it's just a visual look-see. Others are you hover, like for example, if you were to hover over fumarate right now, if we had the software live, it would come up and it would blow up the mass spectrum, and you can actually see the raw data, or the centroided data. You can do a lot of different visualizations with it. In this case, there's a lot of information right here, because if you're looking at it from an entire pathway perspective, there's as much or as little information here as you want. The quilt plot's nice because it shows you the time course on the y-axis, and it shows you our isotopologues on the x. So we can see that at 0 hours, based off the dark red color, we're at no incorporation. And as we incubate, this dark red flips down to a lighter shade of pink as we start to see incorporation in some of the isotopologues. So at this point, we're done doing the technical stuff, and I'm going to actually show you a little bit of data. Are we doing okay so far? So, like I said, I was very happy that this data actually is in good agreement with the data that Gary showed, because I wasn't aware that he was going to present this yesterday. So it's good. I'm really relieved now. But so we're going to talk about a different cell line of cancer, chondrosarcoma, but we're still going to talk about the mutation that occurs in IDH2. And so what we see here, if you look at the TCA cycle, is, and you remember, I don't think, yeah, this slide doesn't do that. But so we start off, and we were curious because we have an arrow that should typically go this way for glutamate as it's uptaken into TCA cycle. But what's interesting is we see and we know that this 2-hydroxyglutarate, or 2-HG, is upregulated. So the question is it going through the TCA cycle and being spit out at the alpha-ketoglutarate step, basically? Or is it going by some other pathway? Maybe it's going to the right, maybe it's coming from over here somewhere. Is it an unknown pathway? How's this occurring? And so with some, as I mentioned, this is in collaboration with Justin Cross at Memorial Sloan Kettering. And so they did the cell line, they did the data analysis, and they were kind enough to let us work up the data. And we're actually going to have an app note on this. So if you would like to see this in greater detail, there will be a note I can send you on it. So the tracer in this case is fully labeled glutamine, and we monitored for all the metabolites you see here in green. So anything that's in green means it's something that was on our targeted metabolite list. So the 2-HG results show that we did in fact have incorporation. You can see the mass spectra over here, and again on the right, you can see our isotopologue data showing that at 8 hours we actually had incorporation of an M+5 isotopologue into the 2-HG metabolite. So it does say that there is flow going from fully labeled glutamate into 2-HG. And there's several ways that we can summarize this data on the pathway. Some are quick, as I mentioned, and these are some of the ones that are very visual, very immediate. That gives you some basic information about what's happening on your pathway without having to do a lot of digging. So first one on the left here, this is just abundance. So it's a very good practice to know in any set of experimental conditions what your metabolite pool is doing. Is it going up? Is it going down? So this is strictly abundance. There's a middle one here where we can monitor and, based off the color, give a stable labeled isotope incorporation. So was there label flowing into this metabolite, or was there not? When we look at the pathway visually, we just quickly tell. And then we can actually do both and say there is change in abundance and there was incorporation present. And so for this experiment, we basically are able to show that there is both incorporation and change in abundance in 2HG. So if we go on and look at this a little bit further, here's our quilt plot again. And we can see, same thing, we see incorporation into the N+5. What's interesting is there's not very much, if any, at 8 hours in the N+4. So we'll talk about that a little bit more in a minute. But another piece of visualization that actually provides you with a lot of information in a hurry is a fractional labeling plot. And so we can see, the relative percent of incorporation across the time course. And so we can say that at 8 hours, roughly 60% of all of the 2HG was fully incorporated, had label present. So another visualization, which is not related to 2HG, but is still useful to have, and it just outlines some of the the visualizations you can use, is to look at basically you're visualizing the results you saw in ProFinder, but this time in context of the pathway. And so one of the other metabolites that we looked for in our targeted list was oxidized glutathione. And so we can see what's happening to some of the other, pathways or the other metabolites downstream, and we can see that there is uptake of the 5-carbon labeled glutamate in oxidized glutathione, and we can see that. It'll help if I actually point at the right one. And we can see that we're actually seeing one 5-carbon labeled building block here and another one, and we can actually see as this trickles through. So at 3 hours, the first N+5 was the highest abundance, and at 8 hours it was actually down because it had already made it in a second incorporation. And again, the node field up here just shows, based on the intensity of the color, lets you know how intense the metabolite pool is. So if we step back now and we look at this more globally, we've kind of gone and we've zoomed in and we've seen some of the nodes, we've seen the quilt plots, fractional labeling. Now if we splatter it all on here at once, we can see our pathway. And what we've done is we've taken and we did the data analysis, we created our pathway using Omics Premium, so we loaded in content from KEGG, I believe it was KEGG or BioPsych, maybe in BioPsych. So what's nice is you can take and we put in glycolysis here, but we didn't put all the metabolites here. We want to know where it is, and we can expand out glycolysis and look at those metabolites if we were monitoring them, and then consolidate that back down if we want to have a little bit cleaner pathway. So we've generated our pathway here, and we've been able to give some biological relevance to our data, right? And we've done this all in about a couple hours. So what's interesting is, I mentioned that we're seeing 2-hydroxyglutarate as a 5-carbon labeled entity, right? So we were not seeing very much, if any, of the N+4. And so if you were to think about this, if glutamate was coming in a normal pathway, or normal entry point into the TCA cycle, it would enter right here, and you would immediately go from a 5-carbon to a 4-carbon succinyl-CoA as 1 carbon is fully oxidized and blown off as CO2. And then we would go around the pathway as 4-carbon labeled and 1 naturally abundantly, 1 C12 labeled. And so we would come around here, and then we would form 2-hydroxyglutarate as a 4-carbon label instead of a 5. But yet, until we get out to the very, very, very late time points, do we see any of the 4-carbon label? We'll eventually see it, but as you saw in Gary's data yesterday, it's very much gives you the idea that the dominant pathway is actually coming in and turning to the right, because the 2HG mutant enzyme has, it's basically a gain of function phenotype, and so you're actually more efficiently able to produce 2HG, which leads to a lot of biological ramifications that I won't get into right now. But it's it's the premise of a lot of cancer cell research right now. So with that being said, I think that's all the jargon I had on that slide. So I'll just kind of give a little bit of a summary in terms of of what solutions are in the core right now, because all of these tools that I've described, short of the software that we just talked about here, are already available to you, and the ability to do flux analysis will become available in the next few weeks or so. And so, Agilent has for a long time had most of the solutions that you need for metabolomics. So that's LCMS, GCMS, and CEMS. And it's based on a lot of the things we've talked about: dynamic range, isotopic fidelity, things that we've engineered into our instruments to give them a good opportunity to analyze this data properly. We've developed some ProFinder software. And then we've recently extended it to now do flux analysis. Metlin is available in the lab, so you can do all the referencing to a library for doing targeted analysis. And in the event that there's no library hit, we have a piece of software called Molecular Structure Correlator that will help you piece together MS-MS spectra without a library match. And then if you didn't take a tour of the lab, this is basically what it looks like. So most of this stuff is in the lab already. Maybe not a couple of these GC-MS systems, but the vast majority of the technology that Agilent would use and prescribe for metabolomics is already available in the lab. So with that, I think we've got just a few minutes left for any questions, and hopefully you're still awake. Yes, ma'am. Mm-hmm. Yep. No, so right now there is no mixing function. It's single label. Although I do know that some of our collaborators have done the dual labeling and then done the targeted feature extraction, C13, taken the same data set back and run it as N15, and they actually said that the data looked very nice. I can't really comment on that further right now because we haven't done very much internal testing on that. But that was the comment from one collaborator, that they didn't actually have a problem with it. So, yes, ma'am. So you're talking about doing like just a pairwise statistical comparison? Mm-hmm. Mm-hmm. Yeah, so if I understand your question correctly, at this time, we are doing basically an ANOVA for that kind of a characterization. So I didn't show it in here, but there's basically a way to do like a student t-test within Omics Premium, and you can also do an analysis of variance for multiple data sets. So I believe that's where you would do that kind of a comparison. Does that work or no?